Okay, so we learned about heat, then we learned about work done, then we learned about the internal energy, which is this. Then we learned about the entropy and uh, what else did we talk about? Actually, we talked about quasi-static and reversible transformation. Okay, so we were doing this thing last time. That this one stands for irreversible processes and equality stands for reversible processes. Reversible, reversible cyclic. And for this reversible one, we saw that T cross Q by T, A to B is path independent. For reversible transformation. The question is, so let's see what happens if I make the cyclic process irreversible. Okay? So that is to say, let's say I go from A to B along path, A to B along path 1, which is reversible. But I come back from B to A along a path which is path 2 and which is irreversible. So I go this way reversible, this way irreversible. Then of course the whole cyclic process is irreversible. So if I apply this, then what I will get is I will get A to B along path 1 of T cross Q by T plus B to A along path 2 of T cross Q by T, but this is less than 0 now. Why? Because one path is irreversible, that makes the whole cyclic process irreversible. So therefore, I need to take into account the negative, the less than symbol here, the inequality here. But again, what I can do is that I can bring that to the other side. If I bring that to the other side, this one, if I bring this to this side, then what I get is this. Less than minus A I P but this one, see, only path 1 is reversible, path 2 is not reversible. So therefore, this one is irreversible. Maybe it is not irreversible. So because path 1 is reversible, so this guy, I can change the integration and make it into a plus sign. That is what I do is that I make it plus, make it A, and make it B. Why? Because this path is reversible, so therefore I can just flip sign and change the integration limit. But what is this guy? B to A along path 1 D cross Q by D, but this path is reversible. So this, the right hand side is nothing but, I just use this one. So it is B to A of ds, which is nothing but SA minus SP. So therefore, I get an important inequality here. is that if I go from A to B along an irreversible path and compute this quantity is less than the entropy change that will take place in going from A to B, which is this. So therefore, for an irreversible process, T cross Q by T, when I integrate from one point to another, for an irreversible process, this integral is less than the entropy change between the 2 points. While for a reversible transformation, T cross Q by T, this integral is exactly equal to the entropy change between the 2 points. I guess there are more things that I need to cover, but I think it would suffice if I stop here and go to statistical mechanics. So from here, what we know is that D cross Q by T is equal to ds, and the first law of thermodynamics tells me T cross Q is equal to du plus pdv. So therefore, I can combine these two to write for a reversible process that TdS is equal to Du plus Pdv. So this is the familiar form of the second law of thermodynamics. There are more things that we need to consider, but I think at the moment, I think I want to move on to, just on the basis of whatever I talked about, I want to move on to statistical mechanics. So in statistical mechanics, you ask the following question. So I told you about the first law of thermodynamics, second law of thermodynamics. I told you that these are laws, you cannot prove them, these are not theorems. But then we stated these laws, but we do not know how to express the heat in terms of the coordinates and the momenta of the particles. We do not know how to express work, internal energy, entropy, any of these thermodynamic quantities. We do not know how to express them in terms of the coordinates and the momenta of the particles. That is, we have to somehow reconcile or bring together this framework of thermodynamics with that of classical mechanics. In classical mechanics, we know we talk about energy, momentum, coordinate, potential energy, but those quantities are not appearing here. Instead, we are encountering new quantities like the work done, the entropy, the internal energy, and the question is how to, bring them together. What is the connection between work done, internal energy, entropy, etc., with notions that we are familiar with from classical mechanics, let's say positions, momenta, total energy, kinetic energy, potential energy. So that bridge between classical mechanics and thermodynamics, that is microscopic description given by the Newton's laws of motion. Let me just write it down here. On this side, I have a microscopic description, basically Newton's laws. And on this side, I have macroscopic properties. And if we have thermodynamic laws, we have to somehow form a bridge between the two. Okay, so the two have to be somehow reconciled with one another, and that is done by the subject of statistical mechanics. And this is what we are going to learn in the rest of the course. Okay? So let's then start with statistical mechanics and see how we can reconcile the two things. Okay. So we start with formal statistical mechanics. So we want to start from classical mechanics. If you recall, in classical mechanics, we always deal with isolated systems. Systems which are described by a Hamiltonian for which energy is a constant of motion. The energy does not change as a function of time. So we are going to start from that premise. Namely, we consider an isolated system with n particles contained in volume V and with total energy equal to E. And which is this, and n, as we mentioned, n is of the order of the Avogadro number. So it's not one or two particles, but very many particles. And this volume is much larger than atomic volume. And E is the total energy. So we are in isolated system in 3 dimensions. Let me denote by I and Qi. So these are the momenta and the coordinates of all the particles. So how many particles are there? I have n particles. For each one of them, I have 3 values of momenta and 3 values of coordinates. So therefore, in total, I have 6 n real numbers. Okay. So because I have 3 n momenta and 3 n coordinates. If I combine the two, I have total 6 n variables to deal with, which I denote by this quantity PIQI, where I runs between 1 and 3n. 3 because I'm in 3 dimension and okay, I have 8 particles. Therefore, the Hamiltonian of the system, I can write it to be a function of all the PI's and the QI's. And I know how do the equations of motion look like. They are given by the Hamilton equations. Pi dot is minus del H del Qi and Qi dot is del H del Pi. What we will do is that we will try to make the theory very general. So in doing so, what I can do is I can say that the energy of the system, let's say, how do I measure the energy of the system? I measure the energy of the system with the help of some apparatus. Okay, so that apparatus will have some precision. Okay, it will not give me exact answer. It will have some error. So let me incorporate that error by saying that the energy of the system lies between E and E plus delta. Where delta is a small number that is much smaller than E. And if you are dealing with a situation when delta is equal to 0, then this theory is general enough that you can put delta equal to 0 at any point in the calculation. Nothing will happen. So then we introduce this concept of macro state. What is this macro state? Macro state is whatever you need to specify to describe the system at the macro level. Macro level meaning observable level, something that you can observe with your eyes. So at the level of, let's say, observing with your eyes, you cannot see the coordinates and momenta of the particles. But then what you can see is definitely the number of particles, the volume V, and the energy that lies between E and E plus delta. So these numbers, they define the macro state of the system. How about the micro state of the system? Micro state is whatever you need to specify to describe the system at the microscopic level. So of course, at the microscopic level, you need to tell me the values of the coordinates and the momenta of all the particles making up the system. So therefore, microstate is given by this. So these are the two notions that we encounter, macro state and micro state. So the next notion that we need is the following. Given a macro state, one can have many microstates, many microstates. This is quite easy to see because if I fix the value of energy, then you can come up with many different combinations of the momenta and the coordinates that will give me the same value of energy. Okay. So suppose I tell you that the coordinates and the momenta, they have these values. Then this inequality, it leads to an equation of this sort. Right? Because it says that the total energy of the system has to lie between E and E plus delta. So this, and if I solve this, I will get many solutions for PIQI. This is exactly what I meant when I wrote this down here, that if I tell you the macro state, you will have many different microstates. Not just one microstate, but many different microstates. Okay. In fact, typically the number of microstates that you will get will be exponentially large. It will be exponential in the number of particles. So given that for a given microstate, you have many different microstates, a convenient way to represent the microstates is to introduce the notion of a phase space. So what is a phase space? So a phase space, it's a 6n dimensional space whose axis are precisely the Pi and the Qi values of the particles making up the system. So it's a 6n dimensional space. So I have 3n values of coordinates, 3n values of momenta. So therefore, in this 6n dimensional space, which I represent here, a microstate will correspond to just a point. Why? Because a microstate is defined by 6n real numbers, and so is this space. This space is also defined by 6n real numbers. So therefore, when I say that for a given macrostate, one can have many microstates, it just means that I will have many points here. Each one is a microstate. Each one is a microstate. So these microstates which are consistent with a given macrostate, so there is a name for it, it's called the ensemble. Ensemble is collection of microstates which are consistent, that is, they satisfy the same macrostate. Till now, any question? No question. No question or what?
No questions, sir.
So how can that be possible? That even I have questions. Are you sleeping or what? Hopefully you are not sleeping, right? Please to ask questions, because then it serves no purpose, no? Then I am wasting my time, you are wasting your time. Please to ask questions. If something is unclear, I'm pretty sure something is unclear. So you are spending time, energy to come to this refresher course to attend the lectures. We are also spending time and energy to lecture. So please to ask questions. Don't just be vegetable. Sit there and then go back. No, because that doesn't serve any purpose. Okay. So please to ask questions. Okay, so we have understood the notion of a phase space. So there is a convenient way to describe this ensemble, namely the collection of microstates which are consistent with a given microstate, by introducing this quantity called the phase space density. What is this quantity? This quantity tells me, okay, before I go to that, let me first make one more important remark. Namely, these are all microstates which are consistent with a given macrostate, but each of these points, which represents a microstate, is not going to remain stationary in time. It is going to move around. Why is it going to move around? Because each of these microstates is given by the values of Pi and Qi, but then this Pi's and Q's, they change in time according to the Hamilton equations. So therefore, these points, they are not stationary, they are moving around. And so therefore, if you ask how many points are there in a small 6n dimensional volume element, that number is going to change as a function of time. So therefore, we introduce this quantity called phase space density. What does this quantity tell me? This quantity tells me that at time t, how many microstates are there in a small 6n dimensional volume element around the point PIQ. Okay, so this is a way to characterize the phase space points, because in the phase space you have many points, and so therefore you can talk about density. How many points are there per unit volume here, per unit volume there, per unit volume here, and so on. So the number of points per unit volume that you get at a given time, here, etc. So that defines the phase space density. Okay. So please remember that points here mean microstates, not particles. Particles are of course moving, but each of these microstates is also changing, evolving in time according to the Hamilton equations, and therefore the density of phase space is also changing as a function of time. So then it is interesting to ask, how does this quantity rho change as a function of time? Okay, so this is the next quantity that we are going to look at, and we'll derive an equation for this quantity. So how do I derive an equation? So in the phase space, consider an arbitrary volume in phase space. In the phase space. So although I call it a volume, but actually it is a 6n dimensional object. It's not really, the volume, the centimeter cube, meter cube volume that we have, but it's a volume in the phase space. So let's denote it by omega. And then we ask, how many microstates are there in this volume at time t? So the number of microstates which are there in this volume at time t is by definition given by Qi Pi E. I have to integrate over dqi dpi, integrate over all the qi's and pi's. So therefore I do I going from 1 to 3n. This is the total number of points microstates contained in this volume element, in this volume at time t. And if I ask, how does this number change? Suppose I want to know this quantity. How does this number change as a function of time? This I can, this quantity I can evaluate it slightly differently. That is, what I do is that I first consider the total number of points contained in time at time t, and then I ask how does the number change. Or what I can do is that I can go to individual points in this like omega volume and ask how much does the number change locally, and then integrate over whole volume. That is to say, this guy will be same as this total derivative. When it goes inside, it becomes a partial derivative, simply because this quantity, the integral, is independent of coordinates and momenta, so I can take the total derivative. But when I bring this derivative inside, this quantity depends on time as well as coordinates and momenta, so therefore I need to take the partial derivative. Okay. Now I want to know what this guy is equal to. So it is quite easy to see what this guy is equal to from the following consideration. So I'm given a macrostate. The macrostate is the number of particles is n, total volume is V, and the energy lies between E and E plus delta. So I make a list of all possible microstates, the ensemble. All microstates which are consistent with the given macrostate. Once I have found this collection of microstates which are consistent with the given macrostate, that number is not going to change as a function of time, because I have taken care of all possibilities. So therefore, the total number of microstates is a constant. It doesn't change as a function of time. So therefore, if it so happens that in this volume omega, the number of microstates changed, it has to be that some points came into that volume and some points left that volume. So the difference between the two, which will give me the current, the number of points changing, and the number of points, net number of points entering the volume per unit time, that will give me the net change in the number of points in that volume in unit time. So therefore, this guy will be nothing but the current, which will also be a function of Qi and Pi. This is taken over the closed surface enclosing the volume V with a minus sign. Why? Because J is the current outside. So if current is going outside, net, if there is a net current outside, okay, the number has to decrease. So that's why I need a minus sign. Because if more points leave the volume than points coming in, there will be a decrease in the number of points contained in volume omega, and that's why I need a minus sign. But then what I can J is the current. What is the definition of current? This we know from classical mechanics or from, I don't know, probability theory, quantum mechanics, electrodynamics, everywhere current has the same definition. Current is number of points crossing a unit area in unit time. Okay. So here, of course, the current has nothing to do with particles crossing. The current has to do with microstates that are crossing. Okay. So current has the general formula that this will be, current is always density times velocity. Okay. So what is the density? Density is rho, the same density here, and the velocity is what? Velocity will be, there will be some velocities attributed to the derivative of the coordinates and some velocities attributed to the derivatives of the momentum. Please do recall that these are not velocities of particles, but these are velocities of microstate points. So therefore, this J itself is a 6n-dimensional vector with components given by Q1 dot, Q2 dot, all the way up to Q3n dot, and P1 dot, P2 dot, all the way up to P3n dot. So this is the definition of the current. But now what I can do is that this is the form that allows me to use the divergence theorem in vector calculus. What the divergence theorem tells me is that if I have a vector field A, then A dot in ds, the surface integral is nothing but divergence of A dv integral over the volume which is enclosed by the surface S. So what I can do is that I can convert this surface integral into a volume integral and write this as minus of the volume omega of divergence of J d omega. But d omega, please recall that this is a 6n-dimensional object because we are talking about not volume in physical space, but volume in the 6n-dimensional phase space. Okay. So therefore, I get this equation that with this equation that by I going from 1 to 3n of dqi dpi of del rho del t is equal to minus, so there is this volume omega surfaces equal to, this integral is also over volume, this is also over volume of dV divergence of J. But this dV is nothing but pi equal to 1, 2, 3, and it's just the volume element. So therefore, this will also be equal to this kind. Okay, so therefore, if I combine these two sides, I get an equation that looks like this. This equation is true for any arbitrary volume element omega. I did not specify anything about the volume element omega, volume omega. I just said that it is any volume in the 6n dimensional phase space. So therefore, I have a situation in which I have a function which is integrated between a to b, and you get 0 for all ab. A very similar thing here, that I have an integral, the integral is 0 regardless of which volume you integrate it over. So in the same way, I have a function which is 0 regardless of which interval you integrate it over. So this one has a simple solution, that it has to be that fx is equal to 0 for all x. Because otherwise you cannot have a function whose integral is 0 for all integration. So in the same way, therefore, I can just use this one to say that this guy has to be 0. Otherwise, this cannot be true for any arbitrary volume omega. So therefore, we get this very nice equation, which is known as the Liouville equation. We get this equation del rho del t plus divergence of J equal to 0. A similar equation you must have encountered in electrodynamics, which goes by the name of equation of continuity. So you get the same equation. So let's try to make this equation somewhat simpler by making use of the Hamilton equations of motion. So what I do is that let's evaluate this quantity. So J is what? J is equal to rho times Q1 dot, Q2 dot, Q3n dot, P1 dot, P2 dot, P3n dot. So therefore, by the rules of vector calculus, divergence of J is simply given by this quantity. It is rho times del Qi dot del Qi plus del Pi dot del Pi. I need to sum over I from 1 to 3n. By definition, if you have a vector with x component and y component and z component, then the divergence is just the derivative of the vector with respect to the x component plus derivative with respect to y plus derivative with respect to z. So that's the case for 3 components. Now I have a 6n dimensional vector. So this vector has 6n components. So therefore I have to take the derivative with respect to each of the components, which is exactly this. But I should write the rho here, because rho also depends on PIs and QIs. Sorry, there's a rho factor. Because recall that rho is also a function of the coordinates and the momentum. So therefore, rho is not a constant. While taking the derivative, I also have to take the rho's into account, which is exactly this. But if I now expand out the bracketed quantity here, I will get four terms. I will get a rho del qi dot del qi plus qi dot del rho del qi plus rho times del pi dot del pi plus pi dot del rho del pi. There will be four terms just using the chain rule of differentiation. But these two terms will cancel. This term, sorry, not this term. These two terms will cancel. This term will cancel with this term. Why? Simply because what is del qi dot del qi? Del qi dot del qi is nothing but, so the Hamilton equation gives me qi dot is equal to del h del pi. So therefore this is nothing but del 2h by del qi del pi. This is this term. What is this term? Del pi dot del pi. But pi dot I know what it is. Pi dot is minus del h del qi. Therefore del pi dot del pi is minus del 2h by del pi del qi. And these two terms are just negative one of one another. So therefore these two terms cancel. So therefore I am left with what? This in this summation I will be left with this guy. R equal to 1 to n. Rho I can take out qi dot, which is, sorry, rho I cannot take out, sorry, I'm taking this one. So I will be left with qi dot del rho del qi plus pi dot del rho del pi. Therefore, this equation now looks like this. This equation can be further simplified because qi dot is equal to del h del pi and pi dot is equal to minus del h del pi. So therefore, I get this equation as del rho del t plus summation I equal to 1 to n of del rho del qi del h del pi minus del rho del pi del h del qi equal to 0. But this guy, from classical mechanics, we know what it is. This is just the Poisson bracket of rho with h. So therefore, we get this equation del rho del t plus rho h equal to 0. This is what is known as the Liouville equation. Liouville. What is the utility of the Liouville equation? The utility is the following. That suppose I want to know there is a macroscopic observable, let's say. Therefore, O will be a function of all the Qis and Pis. So therefore, O will have different value for different microstates. So in this space that I have drawn where I have all these microstates, O will have different values for different microstates. And I may ask what is the average value of O. So this is quite easy to see what this average is going to be. So suppose the system is in the microstate QIPI, and if the system happens to be in that microstate, then this is the value. But then, what is the number of points in the phase space with microstate in this, with these values? So that is by definition given by So what I do is that I go to one small infinitesimal volume here. I find what is the number of microstates contained in that volume. That is given by this factor times dqi dpi pi running from I to 3n, number of points which are there, and for each of these points, O has this particular value, and I integrate it over the whole of the phase space. That will give me the value of this quantity O. And since there is an explicit time dependence here, the value that I compute this way, that will also depend explicitly on time. So let us do one small exercise to make this look like a probability. So how do I do? Suppose I take this function rho of qi, pi, t, and I integrate over the whole phase space, not just over a small volume, but over the whole phase space. This will give me, by definition, the total number of microstates. By definition. Which I call, let's say, cal n, curly n. But this total number of microstates, it is a constant, does not change as a function of time. So what I can do is that I can divide a rho by this total number. Okay, so I divide rho by this total number. So then this right hand side will become 1. And I call this guy rho divided by n my new phase space density, which let's say I continue to denote by the same symbol rho. So then the advantage is that rho becomes just like a probability distribution, that a function which when integrated over all possible values of its variables of its arguments, if I integrate it, I get 1, then it becomes like a probability, and then this is exactly like computing the average value of this quantity with respect to that probability distribution. So this endows the phase space density with an interpretation of a probability distribution. what is the probability that the system is found in a given microstate QIPI? That probability density is given by rho of QIPI. Any question until now? So then I move on and come to the microcanonical ensemble. Equilibrium. Till now we learned about this phase space density. That in this case changes as a function of time. Solving this equation. And the third thing is that if you have a macroscopic observable, then its average value is given by this quantity. Now we come to the concept of equilibrium, because recall that we have to reconcile with thermodynamics. In thermodynamics, we were always dealing with time-independent macroscopic properties. So this is a macroscopic quantity because it refers to the whole collection of particles. And so now we have to see how can we make it time-independent. So if I want to make this right-hand side, left-hand side time-independent, the only time dependence that appears here is here. Okay? So therefore, in equilibrium, somehow I have to make rho time independent, because if rho becomes time independent, then the macroscopic observable will also have a time independent value. So this means the value of this guy in equilibrium will be given by the same integral, excepting that rho has to be time independent. So let me call it rho equilibrium, which will of course depend on the coordinates and the momentum, but not on time. So rho becomes time independent. So therefore, if I look at the Liouville equation, this term goes away because rho is time independent. So therefore, rho equilibrium satisfies this equation. So therefore, an equilibrium state is a very special state. Namely, it is a state in which the free space density also commutes with h. If I take the free space density and compute the Poisson bracket of rho with the Hamiltonian, I should get 0. And this defines my equilibrium state. So it's a very special state. And in an equilibrium state, just as in thermodynamics, if I measure the value of a macroscopic observable, I'm going to get a number that is time independent, that does not depend on time. Okay? Therefore, rho equilibrium, it is such that rho equilibrium also commutes with h, And in this state, O has the macroscopic observable has got a time independent value, which I call O equilibrium. Now I can think of many different ways to satisfy this condition. Okay? So one simplest way is to have rho equilibrium equal to constant. And this will satisfy this equation. So this brings us to the notion of the microcanonical equilibrium. Remember the setting that we had started out with. We had a system which was isolated, contained in particles volume V with energy E plus delta, and the system was isolated. So what is this microcanonical equilibrium? It says it is a form of rho that of course corresponds with H. So this is just a constant. So the space density, which is a function of Qi and Pi. This is a constant, of course, if this microstate is consistent, that is, the energy of the microstate lies between Qi and Pi, E and E plus delta, and is equal to 0 otherwise. Okay, so this is the, so what is microcanonical equilibrium? You take a system, you isolate it from its surroundings so that the total energy is a constant of motion. Total number of particles is not changing, the volume is not changing. And then you ask what is the equilibrium state of this collection of particles. That equilibrium state is what is given by the microcanonical equilibrium. It tells us that for this system in equilibrium, the phase space density is uniform. That is, if I make a list of all possible microstates and I put them as dots in this 6n-dimensional phase space, then I'm going to get a uniform density. I'll get as many points here and here and here and here and here. Everywhere I'll get the same number of phase space. Okay? So this is the definition of a microcanonical equilibrium. Now let's fix the value of this constant using the normalization of rho. What will be the value of this constant? I know that rho equilibrium Qi Pi dQi dPi. Let's first do this integral. First, energy has to lie between E and E plus delta. According to this formula, this could be what? This could be just, this is just a constant. So let's call that constant C. So C times integral of pi equal to 1 to 3n of dQi dPi H between E and E plus delta. This is equal to 1 by definition, because the function is normalized to 1. So this at once fixes the value of the constant C to be, C will be nothing but 1 divided by this integral. This integral, let me denote it by this symbol gamma. Let's find out what are its arguments. So its arguments are, of course, the total energy, the number of particles, and the volume. These are the constants of motion. So therefore, this integral, it is a function of all the constants of motion, the things that do not change as a function of time. So therefore, combining everything together, what we find is that the microcanonical ensemble is given by these formulae. Microcanonical ensemble phase space density is given by QIPI is equal to 1 divided by gamma in VE if it's a consistent microstate, that is if the energy of the consistent microstate lies between E and E plus delta and is equal to 0 otherwise. So this defines the microcanonical ensemble. Okay, any question up till now? This is what we found, and then came the genius of Boltzmann, who said, okay, everything is fine until now, but how do I make connection with thermodynamics? So he said that the entropy that we had defined earlier, we found that it is a state function, it doesn't depend on path. He said that this function is nothing but KB log of this kind. That is, you take the plus and additive constant. So up to an additive constant that is immaterial, the entropy of the system is given by KB log of gamma in V. Where gamma in V is the integral that I have defined. If the gamma in V is just the number of consistent microstates of the system. So therefore, given a system, how do I study thermodynamics? The first thing that I have to do is to know its Hamiltonian. Once I know its Hamiltonian, and I know the total number of particles and the total energy and the total volume, I find this quantity gamma. Once I know gamma, then everything is set. I just multiply, take the log of that gamma and multiply by a constant Kb. This is going to give me the entropy of the system. And once I know the entropy, then I know all the thermodynamic parameters of the system. Why? Because what I do is that once I know this entropy function, then I use the second law of thermodynamics. The second law of thermodynamics tells me that TdS is equal to du plus d bar w, and d bar w is nothing but pdv. This we saw in the first class. Okay? So therefore, I get this equation PdS is equal to du plus PdV. And now I know how to relate the temperature to. So what is T? T will be equal to del S del. You see S, let me just make one step more. S will be a function of NDE because this is a function of NDE. It becomes a function of NDE. So the first identification that I have to do is to say that the internal energy is nothing but the actual energy of the system. So if this is so, then this is nothing but dE plus PdV. And so then temperature is nothing but the inverse of the derivative of entropy with respect to E, keeping the number and the volume constant. Similarly, P by T, just take the derivative here, you get the derivative of entropy with respect to volume, keeping the number and the energy constant. So now I have a complete microscopic a complete connection between the microscopic world and the macroscopic world. At the microscopic world, in the microscopic world, I have the Hamiltonian, the coordinates, the momenta. Once I know the Hamiltonian and the coordinates and the momenta, I compute this guy, the number of microstates. Once I know this one, I take log and multiply by kV, I get entropy. And once I know entropy, then I can compute using the second law of thermodynamics, any thermodynamic parameter, pressure, temperature, etc., by taking the suitable derivative of entropy with respect to its arguments. In fact, okay, maybe let me not get that far. Are there questions on this point?
Sir, one doubt, sir.
Yeah.
Sir, you assumed a Hamiltonian, right?
Ah.
Suppose we don't have Hamiltonian.
Then you don't have this one. Then you have what is known as a non-equilibrium statistical mechanics. This formalism starts from classical mechanical description of the system. If you don't have Hamiltonian, then you do not have the Hamilton equations of motion. Yes. And this formalism will not go through. You have a different formalism. What goes under the name of non-equilibrium statistical mechanics. But then you have to do everything afresh. You cannot take any of those stuff that I did here over there.
And this assumes natural Hamiltonian, like sum of kinetic energy and potential.
Yes, usual Hamiltonian.
Suppose we consider velocity dependent potentials like that, still it works.
So long as it has the Hamiltonian structure. See, the only thing that I used here is the constancy of the total energy. So if the energy is constant and if the system is described by a Hamiltonian with Hamilton equations of motion, the explicit form of the Hamiltonian doesn't matter.
Okay, thank you.
In that sense, it is very general. The theory is very general. It doesn't care about the microscopic like details in the sense that, you know, how does the Hamiltonian depend on coordinates and velocities. That it doesn't care about. It just cares about the Hamiltonian structure.
Actually, why I'm asking, we may not know Hamiltonian, but still it may be a conservative system, right?
Yeah, of course, you may have such a situation. You have to do it differently. You have to do it on the basis of dynamics. I mean, you have to write down what is known as the master equation approach. That, okay, you may have some constants of motion, but then you have to tell me how do you update the configurations. In the Hamiltonian structure, you update the configurations according to the Hamilton equations of motion. But if you don't have the Hamiltonian, you have to tell me the rules. How do things evolve as a function of time? Once you tell me the rules of how things evolve as a function of time, I can develop the theory. Here I am taking the rules of evolution to be given by the Hamilton equations, but if the rules of evolution are given by some other theory, something else, then you have to tell me the rules. Then I can develop the theory.
Okay, sir. Okay, thank you.
Okay, any other question?
Hello, sir. This is Krishna here.
Yeah.
My doubt is regarding this equation S is equals to KB ln gamma.
Yeah.
Does this tells you something about tendency of a system to go towards equilibrium?
What, sorry, no. See, these are all time independent properties. They cannot tell you anything about time dependent phenomena. What you need to do in order to understand time dependent phenomena is to look at this equation, the time dependent equation. You have to study the time evolution of rho. But we did not do that. We said that we are in equilibrium, therefore the first term is 0 and you are left with only the second term. If you want to know how the system approaches equilibrium, you have to study this time dependent equation.
Okay, sir.
So we are assuming that we have already reached equilibrium. Okay? So, but for example, if you ask how does the length of this chalk change as a function of time, then you have to study this time dependent equation. But we are looking at the color of the chalk. The color is the same regardless of the length. It's a time independent phenomenon for which you have this equilibrium statistic.
Hello, sir.
Ah,
Praveen here.
yeah.
Sir, can you give more idea about how micro-canonical ensemble relate to the principle of this entropy?
Related to principle of entropy.
Yeah.
What is that?
So you have taken entropy and you have related the
Oh,
micro-canonical.
no. So this is an ad hoc definition. This is an ad hoc definition. What Boltzmann showed is that if you take this definition, then only you can reproduce the whole of thermodynamics using statistical mechanics. You see, you have to look at it this way, that thermodynamics are experimental facts. Thermodynamics encapsulates, encodes experimental facts. So you cannot violate experimental facts. Your theory should be such as to incorporate all experimental facts. Boltzmann showed only if you define entropy this way that you can reproduce all the experimental facts. Any other definition will not work. You see, there is always a constraint on a theory that you develop. A theory cannot be anything. A theory has to respect and satisfy experimental facts. Thermodynamics has already told us what are those experimental facts, and therefore, your theory has to somehow build in a structure so that you are able to reproduce those experimental facts, and this is done by this definition. This definition is so profound, and there is no microscopic explanation of it. Okay, so this definition is so profound that on the graveyard of Boltzmann, when he died, he was an Austrian scientist. On his graveyard, this is engraved: S is equal to K log omega. If you go to Vienna and visit his graveyard, you will find that it is engraved there. So it is an ad hoc definition, but it does magic. It is able to reproduce all the known facts about experimental all known experimental results.
Okay, sir. Thank you.
Any other question? Good. So this is exactly what I want, that you ask question, whatever. See, no, as they say that no question is a dumb question. An answer can only be a dumb answer. Okay, if I give you an answer that doesn't satisfy you, that can very well be true. But no question is a dumb question. So please feel free to ask questions, whatever comes to your mind. You may think others will laugh at you if you ask a question. Others will anyways laugh at you. Whatever you do, even you get a Nobel Prize, people will laugh at you. What do? You stop living or what? Okay, you live your own life. You ask whatever question comes to your mind. I may give you a dumb answer, okay? But you ask whatever question comes to your mind. Okay. Okay, so what is the time now? Perhaps it is a good time to stop, maybe. There are 4 minutes left. So maybe I just quickly tell you what are my what do I plan to do tomorrow? What I plan to do tomorrow is the following: that using this statistical mechanical picture, this ensemble and microcanonical ensemble and so on, I will derive for you tomorrow the ideal gas. So this will convince you that the theory is good in the sense that it is able to reproduce known experimental facts. It is not violating experimental. If it violates experimental facts, then the theory is no good. You have to come up with another theory. Because physics is an experimental subject. You cannot have a theory that has not been tested in experiments. So you have to somehow be able to test that. And people have already done those tests in thermodynamics. So therefore, your theory should be able to reproduce those results. And one profound result is the ideal gas law. So therefore, using the prescription that I talked about, namely, I first compute this guy NVE, then take log and multiply by KB, and then I get S, and then P by T is equal to del S del V, and 1 by T is equal to del S del E. If I do all these steps together, I should get this back. If not, my theory is bad. It should go to him. And if I am able to reproduce it, my theory is good. Okay, so this is what I'm trying to do tomorrow. And then we will talk about canonical and grand canonical. Okay. So perhaps it is good to stop here.
Yes, sir.
Okay. Okay then. Thank you very much for your attention.